Hi, this is Tim Shu from San Jose State University, and I'm going to talk today about hyperbolic trig functions. So after talking about the goals of this video, we'll talk about the hyperbolic trig functions, some identities about them and their derivatives, and the same for the inverse hyperbolic trig functions. Okay, so what I want you guys to get out of this video? Well, in this video, we're going to define the hyperbolic trig functions. We're going to list a bunch of formulas about them. Most of them, and the thing to remember is that most of them resemble formulas for the regular trig functions, but from an alternate universe. Woo! I mean, they sort of resemble the other ones, but slightly different. And depending on what your instructor wants, you may or may not be required to memorize or even know these formulas. But at this point, however, I think for me, I think the key test is that you should ideally be able to derive almost all those formulas yourself from the definitions of sinh and cosh, which we'll see in a minute, from the definitions of those two hyperbolic trig functions. And it's because, in my opinion, that's the real test. So, at this point, you should be independent enough on your own that you should be able to take just those two initial definitions and run with it. So, fly and be free, my friends. Okay, well, anyway, we'll go through them a bit anyway. All right, so the hyperbolic trig function. So sinh of x, so this thing is pronounced sinh, and this is pronounced cosh. So sinh of x and the cosh of x are defined to be, the sinh of x is defined to be e to the x minus e to the minus x over 2, and the cosh of x is equal to e to the x plus e to the minus x over 2. And tanh, cotanh, and sech and cosech, by the way, I just sort of really, after tanh, all of the pronunciation of the other three ones, I just sort of made up. Various sources seem to disagree, so tanh, cotanh, sech, and cosech are probably good enough as anything. Anyway, those are all defined in the usual way as you would for the regular trig functions. So tanh is sinh over cosh, cotanh is cosh over sinh, sech is 1 over cosh, and cosech is 1 over sinh. If you erase all the h's, everything over here would be very familiar from regular trig functions. All right, so just to talk about hyperbolic trig identities, well, we're really only going to talk about one of them. It should really be a hyperbolic trig identity, and that is cosh squared minus sinh squared is equal to 1. So remember, for non-hyperbolic trig functions, this is cosine squared plus sine squared is equal to 1. And for hyperbolic trig functions, it's similar, except you have cosh squared minus sinh squared is equal to 1. And there are, like I said, there are other identities, but that's the really important one for our purposes. And so why is that identity true? Well, let's consider cosh squared minus sinh squared. Well, if you remember, cosh is e to the x plus e to the minus x over 2, and sinh is e to the x minus e to the minus x over 2. And so if we plug that into cosh squared minus sinh squared, we get e to the x plus e to the minus x squared, quantity squared over 4, because we had that over 2 all squared. And similarly, sinh squared becomes e to the x minus e to the minus x, quantity squared over 4. All right, so that's just plugging in the definitions of cosh and sinh. Multiplying out each of those squares, we get e to the x quantity squared plus 2 times e to the x times e to the minus x plus e to the minus x squared, all that over 4, minus, well, the same thing except having a minus 2 instead of a plus 2. And the reason I'm writing all this stuff out is that almost all of it cancels. The e to the x quantity squared cancels out the minus e to the x quantity squared, and same for the e to the minus x quantity squared. But this middle term, the cross term, 2 e to the x, e to the minus x, reinforces because it's minus 2 times that stuff. And so you're left with 4 e to the x times e to the minus x over 4. And so all that stuff cancels out, and you get 1. Da, 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 da. Yep, cosh squared x minus sinh squared x is equal to 1. All right, so now we come to the derivatives of the hyperbolic trig functions, and those are the derivative of sinh is cosh, the derivative of cosh is sinh, the derivative of tanh is sech squared, the derivative of cotanh is minus cosech squared, the derivative of sech is minus tanh sech, and the derivative of cosech is minus cotanh cosech. And you should, I hope you recognize a lot of these formulas from the regular trig functions, and they're all sort of the same as the regular trig functions, except that some of the pluses and minuses are different. Remember, for the regular trig functions, the derivative of sine is cosine, the derivative of cosine is negative sine. Well, here you have a plus, and sort of once you know those two facts, all the other ones follow in exactly the same way as the derivatives of the regular trig functions. Like I said, almost all the same as the regular trig functions, but with some sign changed. And so if you to derive these formulas, we start by calculating the first two directly. So what's the derivative of sinh? Well, by definition, sinh of x is equal to e to the x minus e to the minus x over 2. When we take the derivative of that thing, we get e to the x over here, and minus derivative of e to the minus x, which is e to the minus x times minus 1 for the chain rule factor of the minus x on the inside. And so when those two minuses cancel out, we get e to the x plus e to the minus x all over 2. And what should that be? Lo and behold, that just happens to be the definition of cosh x. Anyway, so the point is, you can derive this other formula in a very similar way, the derivative of cosh. And once you know the derivative of sinh and cosh, you can use the definitions of tanh and cotanh and sech and cosech. Remember, tanh is sinh over cosh. And so if you use that in the quotient rule, then you get the derivative of tanh is sech squared, and so on. The rest can be derived using the quotient rule. And the key, and the key hyperbolic trig identity mentioned earlier, which is, remember, is that cosh squared minus sinh squared is equal to 1. Anyway, that being said, there they are. And we leave that as an exercise for you to figure out all the other 5 formulas. All right, so now turning to inverse hyperbolic trig functions. These are actually easier to define than the regular inverse trig functions because sinh and tanh are one-to-one functions. Cosh still isn't a one-to-one function, but if you restrict this domain to x greater than or equal to 0, it is. And so we can define that the inverse sinh of x to be by saying that the inverse sinh of x is equal to y exactly when the sinh of y is equal to x. The inverse cosh of x is equal to y exactly when the cosh of y is equal to x and y is greater than or equal to 0. And the inverse tanh of x is equal to y if and only if the tanh of y is equal to x. So again, the only time we had to do this domain restriction and then afterwards the range restriction is in the case of cosh, and there it is. I want to apologize for the awkwardness of the corrections on this slide. All right, and so what are the derivatives of the inverse hyperbolic trig functions? Well, I have to say you don't often see the inverse hyperbolic trig functions except exactly in this circumstance because they happen to have interesting derivatives. So without further ado, we see that the derivative of inverse sinh is 1 over the square root of 1 plus x squared. The derivative of inverse cosh is 1 over the square root of x squared minus 1. Sorry about that. Back to your regularly scheduled program. And the derivative of inverse tanh is 1 over 1 minus x squared. And these are derived using the usual ideas that you use to derive the derivative of an inverse function. So for example, suppose y equals the inverse sinh of x, then we know that by definition x is equal to the sinh of y, and so if we take the derivative of both sides of x equals sinh y, we get 1 is equal to the cosh of y. Remember, the derivative of sinh is cosh. And so we get 1 is equal to the cosh of y times dy dx. And remember, since cosh squared minus sinh squared is equal to 1, we see that cosh is equal to the square root of 1 plus sinh squared, again, times dy dx. And remember, we started off this whole business by saying that x is equal to sinh y, and so we can substitute that in and get the square root of 1 plus x squared. And the formula that we want, that the derivative of the inverse sinh is equal to 1 over the square root of 1 plus x squared. That follows by solving for dy dx. Well, this goes over here in the denominator, and we get dy dx equals 1 over square root of 1 plus x squared. All right, go figure out the others yourself. It's exactly the same idea. You use what you know about the derivatives of cosh and tanh and a bit of those hyperbolic trig formulas. All right, that's enough for now. Go do something useful. Bye.